the goal was to showcase the ability to reform these feedstocks into producing hydrogen. And the CO2 that has been generated, it's there as a byproduct. But if required, we could add a CO2 capture modeling that we're currently working on. So we could couple both of them and integrate them to showcase you could do the CO2 capture along with hydrogen production.
Welcome back to another episode of GT Tech Talk. I'm your host Lalit, and I have with me co-host Ahmed. And today we are going to talk about hydrogen reforming. And to dive into this topic, we have two in-house experts, Deiva and Harish. We're excited to have both of you here on this show. And why don't you introduce yourselves and we'll get into the topic.
Sure. My name is Harish. I joined GT in 2021, so it's about 3 years now. I work as an application engineer in the Reactive Flow group, and I've worked on technologies related to after-treatment systems, reformers, and evaporative emission systems. I'm excited to be on this podcast. I've been watching previous episodes, so I'm glad to share my expertise on this reformer technology.
Great. Hi. Hi, I'm Deiva. I've been with GD since 2022. I'm an application engineer in the same Reactive Flow team, Harish. I'm primarily working on US DOE project on engine after treatment, heavy duty and medium duty. Along with that, in also working on some battery thermal runaway side, chemistry side of it, and some after treatment modeling. So, I'm excited to be here. Thank you for having us.
Yeah, awesome. We're excited to have you. So without further ado, we'll jump into it. Hydrogen production plays a big role in the energy landscape, and there's a lot of interest in using hydrogen for many different applications. So could we start by you giving us a brief overview of the current global hydrogen production landscape, and then kind of the challenges that the industry is facing?
Yeah, sure. I can take that one. So right now there are majorly three technologies, three processes that are used for producing hydrogen globally. First one is reforming process. The second one is gasification, and the third one is electrolysis. Right now, about 2/3 of the global hydrogen production comes from steam methane reforming using natural gas, and then the remaining 1/3 comes from coal gasification, and a very small percentage from water electrolysis. From this comparison, we can see that we are heavily dependent on fossil fuels right now, particularly methane, and that presents some challenges like CO2 emissions. A lot of CO2 is emitted by reforming, and if that is released to the environment, then that can cause global warming. So that's one of the challenge. And then the second one is related to cost. So the cost of natural gas can fluctuate a lot, and that can cause the hydrogen production cost to increase or decrease. So the end customer will face a lot of fluctuations because of that. And then there's transport infrastructure, which is kind of limited for hydrogen because hydrogen was not needed this much before, but now there's a global push for fuel reformers, which majorly require hydrogen as fuel. So there is limitation on the transportation infrastructure side. So these are major challenges.
Yeah, so you mentioned about the three main processes that are used for production of hydrogen. And I believe moving forward, we are going to increase the share of electrolysis. But what are the limitations of that process? Currently, it is contributing very little to the production of hydrogen. So can you talk a little bit more about the challenges with electrolysis and how these reformers fit into this hydrogen production landscape?
Sure. I can go forward. So as you mentioned, electrolysis very little, which is, if I remember correctly, less than 1%, if not even less for electrolysis. And it's not that, yes, it is a tricky process, but the main problem there is it's using electricity. which is one of the costliest or richest form of energy, and you're using that to produce hydrogen. So the main problem there is you need to use renewable electricity, otherwise kind of doesn't make sense, right? So, and we all know renewable electricity is even more expensive. And that's also because the renewable energy itself is not readily available. And so solar or wind or whatever you use, it's very location dependent and everything. So all of this makes the electrolysis more challenging than reformer. So reformer, you could install it and then you can just get started right away. In addition to that, I think there's also really high capital cost and operational cost with the electrolysis compared to reformer. And so that's also making it more challenging for electrolysis to push into the hydrogen production sector as fast as we all would like, despite its advantage on the CO2 reduction or any carbon emissions.
Those are good points that you made about the limitations of electrolysis.
Yeah. I was kind of curious to get an idea, maybe a high-level idea of what the steam reforming process looks like, if you can walk us through those steps.
Yeah. So steam reforming is basically a catalytic reaction of hydrocarbon fuel, like we talked methane, which is combined with steam. And then the catalytic reaction produces hydrogen and carbon dioxide as byproducts. So what happens is the first step is feedstock preparation. So the gas that's going to pass through the reactor. For that, the fuel is mixed with steam. Fuel can be methane or methanol, ethanol, or other hydrocarbons. It's mixed with steam at a particular ratio, and then it's preheated to a temperature depending on what kind of fuel we are using. Then after this pretreatment, it's passed through a reactor, which contains different kinds of catalysts, again, depending on the kind of fuel that we're using. And so when it passes through the reactor is heated at a particular temperature, which is higher than the temperature of the feedstock. And the catalyst and the temperature together, they help these two species, fuel and steam, to react and produce hydrogen and carbon dioxide. And because certain fuels also produce carbon monoxide as byproducts, so that gas. And then once these products are formed, they come out of the reactor and then they are passed through a purification process to remove or isolate hydrogen from the other species. And then we get the pure hydrogen. Yeah, it's like a very general overview.
It's a great overview. And I have a follow-up question. So where does the energy come from for powering this reformer?
So generally, if you take as you mentioned, steam methane reforming is one of the most common. So which requires really high temperature to start with, and it always comes from the external source. You cannot use any internal process to stimulate or initialize. So either external heating with some other natural gas or coal heater, or you need to heat it with electrical heater, which is again not ideal, as we used to talk about the issue with using electricity for this. So it has to be. So this is what is making onboard reforming a bit more challenging because of those high temperature requirements.
And what is the range of temperature that can go into these devices?
It depends on the fuel itself that you use, the feedstock that we talked about. And I think in this particular study, we studied 3 different fuels where the temperature you could see ranging from 300 to 300 degrees Celsius up to 1000 degrees Celsius. So it's a really wide range. And so it depends on I understand I'm using depends, but it really depends on the temperature, catalyst, and the feedstock. So, and the flow rate as well, the flow rate of the feedstock. So all of this directly or indirectly contribute to your hydrogen yield and the purity.
Yeah, so as you've mentioned, you two worked on a paper that was published earlier in the year, and that study you looked at some of the variables that you mentioned, right? A big idea was to explore the different fuels, right? But not only that, you also extended your study to see the effects of flow rates, temperatures on H2 yield. So a very interesting study, and we'll make sure we'll link it in the description for our viewers. That's very interesting. Why don't you talk a little bit about the motivation for that study, and in particular, I'm curious to know a little bit about the differences between the fuels that you chose, right? What you chose and why.
Okay, sure.
I can start.
Sure.
Yeah. So the main motivation behind this study was because we realized that because there's a global push for fuel cells and alternative energy sources for transportation and other things. Fuel reformers were coming up as a technology for producing hydrogen, and people were focusing more and more on that technology. So we decided to show that the GT suite can also do that kind of modeling. And yeah, that's how we started working on the reformer models. And we started with methanol because there was a customer request that came to us that they wanted to model methanol as a fuel reformer. It's like a fuel for fuel reforming process. And we created demonstration model for them. So they got happy with it, but then we wanted to use that as and create an example model out of it. So we worked on it. We found a paper online that had the data necessary for creating an example model. And then the example model was created. And then we saw there are other fuels as well, which I used. So then we started working on other fuels. And that's how the three models were created. We're using methane, methanol, and ethanol.
And this was published in conference or
SAE, SAE earlier this year.
SAE earlier this year, yeah. Maybe you can also talk a little bit about the reception presented.
Sure. I think Harish presented, so
Right.
I'll let him.
Do you want to take the other part of the question?
Sure. So I could wrap up. I think that's where you stopped around. Yeah, we used, as Harish mentioned, three fuels that we used. So started with methanol, and then we moved on to methane because, as he initially mentioned, around 60 to 70% of hydrogen that we have globally are produced from methane. So we know our customer would be happy to see. So we went after more published research, went for methane. Then the third one, we went to ethanol because ethanol is, compared to these two, it's a biofuel, or more readily available biofuel for us. So we wanted to demonstrate that's also possible. Despite its limitation, it has its advantages. So we wanted to do that as well. So we went for that published. We had to go after the publications for us to give us the experimental results. Then we did the modeling and then show a model can predict same trend as experiment. So that's how these three fuel we picked. That's how it turned into a paper. So he can talk about the reception for the paper.
Yeah. So yeah, it was under when I went to present the SAE presentation. Yeah, it was under I think hydrogen and fuel cell technologies. I think that was the topic of the paper. So yeah, there were a lot of different papers, different sections, or we can say different technologies that were presented in that section. So yeah, the audience was mixed, I would say. The people who were there, they asked, I think 4 or 5 questions based on what we presented. So it was good to know that people are interested in this area, which we're working on. And they were curious about GT Suite capabilities as well, how we can model those. And if they want to use it, how they can use it.
Yeah, great. Yeah, it's nice.
Yeah.
So coming back to the fuels, you mentioned there are 3 different fuels that you investigated and potentially other fuels people must be exploring. So for these different fuels, do we have the same reformer technology or do we need different kinds of reformers for different fuels, or is just the operating conditions are different or the catalysts are different? Can you talk a little bit more about that?
Sure. So typically, yes, you need mostly you need different catalysts, and your operating condition will be significantly different. So if we take our three fuels, for example, just to give an idea, so the ethanol, you need at least 700 degrees, before which it was not even reacting. So after 700 degrees up to 1000 degrees, we explored to see different flow rates, how does it affect the H2 yield and stuff. Then for methanol, which is much easier, like, so you could produce hydrogen from methanol at temperatures as low as 200, 300 degrees Celsius at most atmospheric temperature, atmospheric pressure, versus methane required 700, 800 degrees Celsius. So it has a really wide range, and also both temperature range and pressure range. So, and the catalysts are also different for all three.
And a follow-up question on that is, like, what happens to the CO2 that is formed here? Do you capture it and store it somewhere, or are these models inbuilt with the reformer modeling that you performed, or can you talk a bit more about that?
So in our current model, it was the goal was to showcase the ability to reform these feedstocks into producing hydrogen, and the CO2 that has been generated, it's there as a byproduct. But if required, we could add a CO2 capture modeling that we're currently working on. So we could couple both of them and integrate them to showcase you could do the CO2 capture along with hydrogen production, which go back to what Harish previously mentioned about the actual process itself, where they do reforming and then they do the separation process to remove the pure hydrogen. So we could demonstrate the entire thing in our model.
That's interesting.
Yeah. I was wanted to ask you about the variability in the feedstock, and how does that play a role between the different types of fuels that you use. You mentioned pretreatment when we started talking about steam reforming process. How does that look like when we're talking about methane or some of the other?
Right. So the conditions of the feedstock are very crucial for this process. So let's say if we are using methane. Methane usually comes with sulfur. If you just use raw methane, it has sulfur. It can have other poisonous component which can affect the efficiency of the catalyst if used directly. And then similarly, there are other contaminants like soot particles or just solid particles, small solid particles in the feed, then that can also get accumulated in the catalyst and then reduce its efficiency over time. And then the third thing is the water content. So I mentioned that we mix water with the fuel that we are using, and it should be in a particular ratio or in a range of ratios. If it's beyond that, like lower or higher, then that can also reduce the efficiency of the process. So the variability of the feedstock, it has a crucial effect or very significant for this process. But to overcome these challenges, there are certain things that industries do as a pre-treatment. So they do desulfurization, so they remove the sulfur out of the feed. Then they can do dehydration if there is higher water content than what is needed. And they can also remove other contaminants by filtration.
You mentioned about the catalyst poisoning. In our models, is there a way for our users using these models to investigate the effect of the poisoning? Like how much yield you will get if there is a certain amount of contaminant in the feedstock, or your steam is not purely water? Like, is there a way to study this? Can you comment upon that?
Yeah, we do have way that from like a workaround way by which we can model contamination. So just like adsorption of any other species on the catalyst sites, we can model adsorption of that contaminant on the species site, and then we can say that this is not going to be used anymore, that site is not going to be used anymore because it is contaminated by that component. And we do that by surface reactions object that we have in GT. And we do have some example models as well showing that.
That's an interesting approach, and I'm not sure our users will find it useful to model this kind of scenarios and investigate all the possibilities that may arise. Right? during the operation of these systems.
Exactly, because it's one thing to assume that your catalyst is perfect, but practically speaking, your customers are all going to be working with different feedstocks that have their own conditions.
And then these catalysts are used for a long time, so some deterioration is expected to happen.
Yes.
They should be able to model that. If they were modeling, because these reforming processes, they are like steady state. So yeah, they should have that, inbuilt deterioration model.
So as we mentioned in your study, you looked at flow rates, you looked at different fuels, temperatures of these fuels and catalyst loadings. And you were obviously interested in which one gives you kind of the best H2 yield. And I noticed if you were to hold everything constant, generally speaking, temperature kind of had the most effect on H2 yield, but especially relative to flow rates, catalyst loadings, and things like that. Would you agree that that's the case if you were to look at this? And if so, why do you think that is, right? And interested to just hear your thoughts.
Yes, you are right. The temperature has the biggest effect on the hydrogen yield. As we increase the temperature, the hydrogen yield increases no matter what fuel we are using. But the flow rate is another parameter that we observed. If we reduce the flow rate, then the hydrogen yield also increases, but it was not increasing by the factor, like you said, as temperature was showing, but it was still showing significant effect. Now, coming back to temperature, why that was the case, why we were observing so much increase. I think it's prominently because how we define the reaction rates. And then why we define the reaction rates that way is what affects that. Two things. One is in reaction rates, there is a temperature component. So as we increase the temperature, then of course it shows like a direct relation to the temperature. So as the temperature increases, time increases. But in reality, what happens is when the temperature increases, it favors the reaction to happen in the direction of production of hydrogen, because there are different pathways that we can go through for just one fuel reacting with steam. So fuel reacting with steam can produce carbon monoxide and hydrogen. It can produce some other species as well. But with higher temperature, it goes towards the direction of hydrogen production. So it kind of favors that pathway, reaction pathway. And then again, there is activation energy as well. So if there is higher temperature, we can easily bypass that activation energy and even go beyond that. So that also enhances the reaction.
Yeah, and I think I read somewhere as well, and please feel free to correct me if I'm wrong, that some of these reactions are reversible. So if you're not careful about your temperature, you could have the opposite reaction going back to what you started with. Deiva, you wanted to speak a little bit to that, so I wanted to speak.
No, I think he nailed the point. So it's, as you mentioned, it's both dependent on temperature and the flow rate. So that's why we tend to look at the how much time the feedstock could spend at that temperature. So that's why the flow rate matters. So if you have really high flow rates, your residence time drop. So it can't interact with the surface where the catalyst is that much. So that's why you couldn't convert as much as you would like to. So that's why it's important to have reasonable flow rate for that temperature. So that's why both of them affect in the H2 conversion.
I'm sure optimizing these parameters for the reform itself are very important. But I think they are even more important for a broader system level analysis. So where can we plug in this reformer component or technology upstream or downstream in a system level analysis, for example, with a fuel cell or some other components, and what advantages are there in doing this whole system level analysis? Can you share your insights on that as well?
To answer the question, I think you already started with the example of fuel cell, right? So we did study the impact of integrating fuel cell modeling with the reformer modeling. We tried both ethanol reformer and methane reformer. So for the advantage here is by using the ethanol reformer, you can vary the impact of temperature and pressure, and that's going to affect your temperature of the hydrogen that you're producing as well. So if you couple it directly with, let's say, solid oxide fuel cell, which it already requires higher temperature. So by pairing it, you could see the impact of your reformer temperature on your electricity production, so the current production. So that was really good. That is one of the main advantages that we felt when we were able to pair it that way. So in PEM, I think you need to use a cooling effect and stuff to do it. So that's why we studied the SOFC for this integration.
I was curious to know a little bit about how competitive is liquid fuel reformers when you compare it to other processes in terms of electrolysis, in terms of the current market trends when it comes to hydrogen production.
So I think the challenges that we previously talked about with the electrolysis still stands, and we are hoping with the increase in renewable energies and probably nuclear energy impact on the electricity production. So it's going to make our cost of the renewable energy relatively less. So that is going to help us push towards more electrolysis. But again, if we look at it from hydrogen production standpoint, where are we going to use the hydrogen? I think that's the question, right? So if you're going to use it in a fuel cell or something, then this loop doesn't make sense because you're already starting with the electricity. You might as well use it. So you might as well store it in a battery or some other application. So the main reason why you would use it is for industrial application in glass manufacturing or steel manufacturing. That's when you need the hydrogen. So until you are bringing in that cost of electricity that low, it would be difficult to push towards the electrolysis. So that's what is giving the liquid fuel or any hydrocarbon fuel that you're currently using in reforming process the edge, at least for now. And also there are a lot of active research going on in the catalyst side as well. So that's also helping in pushing towards the reforming because it's already slightly cheaper. So you might as well make it more efficient.
In terms of the competitiveness, we talk a little bit about that, the economics of it. I believe the scale also plays a role here. These reforming technologies are much more economical on a larger scale. So are they being deployed on a larger scale, or are we looking at smaller onboard type of applications for these technologies?
I can start. So for now, at least, because these technologies are still onboard reforming, at least it's still coming up. There are few researchers who are working on it. So I think majorly they are done in industries right now. So centralized production kind of, where it's produced in big plants, steam methane reforming processes are done in a big plant, and then hydrogen is transported.
So I think to add on top of that, the onboard issues again comes from your first question of where does the...
When you say on board, what do you mean?
On board as in for transportation application, right?
Yes.
Okay. Yeah. So when you go with the industry side, it is relatively easier to supply that extra energy to heat up, and also it will be a little easier to maintain the temperature of the reactor compared to if you're putting it in a transportation in a vehicle or something, then we need to ask the question of where does that heat comes from. So then you're going to have a penalty on that. So your overall efficiency is going to drop. So I think that's the main reason currently we are seeing it more on the industrial side. But maybe with our push towards the newer catalyst, which could operate at a lower temperature, there could be a potential for pushing it to the onboard if we are moving towards the transportation side.
Right. Just to clarify, onboard is a part of propulsion systems in vehicles. So connected to, so there will be a fuel tank, then a reformer, then passing to the fuel cells.
In terms of regulation, where do you see reformer regulations stand right now? Are there some specific regulations that you think could help adoption or hinder it? What do you think about that?
Right. So overall, I think reformers are kind of in an advantage and a disadvantage as well with the new policies surrounding like reducing global warming. One way is because we are moving away from fuel cells, we want to promote other energy sources, which is one of it is hydrogen, like using hydrogen as fuel. So there are several initiatives by governments or countries like US, Japan, Europe. They are pushing towards these kind of technologies. One that I know about, an initiative by US. It's called Hydrogen Energy. There is Hydrogen Shot is their actual initiative, and it's under a bigger umbrella. I don't remember the exact name. So their goal is to reduce the cost of hydrogen to $1 per 1 kilowatt hour by 2030. So these kind of initiatives, they are expected to increase the demand of reforming technologies. So like researchers are going to research more on these topics and they're going to improve these kind of technologies. But on the other hand, if you look at initiatives such as like restricting the amount of carbon dioxide that can be released or the greenhouse gases that can be released, they kind of hinder the reforming technologies, because then we know the reformers produce carbon dioxide as a byproduct, so they cannot be released into the atmosphere. So we'll have to somehow capture them. And if there are certain regions which do not have these kind of technologies, carbon capture, then they basically cannot use reforming technology.
And you said the goal is to, at least that, as of right now, the goal is to reduce the cost to $1 per kilowatt hour. Do you know how much the current cost is? Off the top of your head, if you don't know it tonight.
It significantly varies from your source.
Right.
So I think that was their average target, and I think it was $2 for 2025 and $1 for 2030. You know, the steps, but it's all projection and policy.
Yeah,
we need to wait.
And according to that policy, they had a goal of reducing it by 80% in 2021. So I think right now it should be around $8.
As engineers, like what are the technical challenges that you are most excited about to solve in the coming future about this technology? What are the challenges that we need to solve to move forward with this technology?
Sure. I think I can take it. So the main thing, as we previously hinted, is the catalyst. So we are been working on a lot of in the recent research, you could see the publications. There are a lot of new catalysts they are testing and trying out. So where they trying to reduce the precious metals they're using, and also reduce the operating temperature requirement. And also, Harish previously mentioned about CO poisoning the catalyst, and you mentioned about the how at high temperature some of the sites will get occupied by the unwanted, so all those things are going to reduce our efficiency. So they're working on different catalysts that could avoid almost all of this issue, like if possible. And so they are in the research field in the last 3-4 years. So as we get closer and closer to that, it's going to improve that. So apart from this, there's also like current work on they call it microreactor or something. So where they try to reduce the size in such a way that you'll have more surface to volume ratio. So that helps with your improve both heat transfer and mass transfer. That's also going to significantly improve your heat transfer. But I think that is currently in a small scale. So we need to wait and see their implementation on the bigger scale.
And just one more point to add. So I talked about pre-treatment. So the researchers are also working on seeing how we can pre-treat the feedstocks to reduce the carbon content in the fuels. So ultimately, they'll produce less carbon dioxide when they react. Yeah. So that's another method of improving these technologies.
All right. Yeah. Thanks for sharing your insights. It was really insightful and a good discussion. And I'm excited about this technology and see how this can help in fight against climate change.
Yeah, thank you for joining us. It was really a pleasure to talk to two experts on it. We're excited to see where this goes. We're excited to see the kind of technologies we adopt here at Gamma. We can provide our customers. It's a lot of interesting stuff going on for sure.
Yes.
Thank you.
Thank you for inviting us. Yeah, it was great to talk about these new technologies that we're working on.
It was a pleasure. Thank you.